Uh, okay, class. So this will be perhaps the last lecture on Lightboard, and we would like to talk about hardenability, Jominy test, and how we can correlate these two concepts together. It's a very important part of this course, and I really hope you master this section because there will be questions in final directly related to this concept. First of all, let's get familiar with the two very common charts we are using. So the first one is the similar to whatever you've seen, obviously. This is the hardness, and that's Rockwell C, could be other units, but usually they use it Rockwell C, versus the Jominy distance from the head. So it's 0, 10, 20, 30, 40, 50, or you have the bottom one, which is inch from 0 to 2 inches. So if you have, imagine that this is the Jominy rod, and then you use red hot, you put it there, and it's cooling down from this. And obviously, the further you are from the cooling head, water splashing from here, so the cooling rate is lower. So that's the meaning of conversion of the distance to a cooling rate. So these are completely related. And we mentioned that it is using ferrous alloy, and regardless of the alloying elements, relatively they have the same thermal conductivity. That's why we don't need to worry about what alloy is this when we go to the actual cooling rate to respect to the cross section. We will talk about that in a bit. So cooling rate, you might say it's not cooling rate. Yes, it is cooling rate. This is the distance from Jominy head. And then in top here, you do have the actual cooling rate. Let's call it 170, I don't know, 70, 35, 2, and so on. So this is a linear. That's the beauty of that. This is not linear. This is degree per second. But they are the same way. The further you go this way, the longer distance or further you get from the Jominy head, then the slower is cooling rate. That's one. And then you have different alloys here. These alloys, obviously, so one of the graph you saw comparing alloys, the same carbon content. 4340, 4110, 8640, 5140, and 1040. 1040 is a plain carbon steel, no alloying element. First thing you have to look at this is, how do I conclude about the hardenability of these alloys? The definition of hardenability is how easily this material can be transformed to martensite. How easily means that how slowly you can cool it and still you get martensite. A really practical way of doing it, I have these two alloys, I have the same size, and then I cool them down with the same rate, and I will see which one get more martensite. The one that get more martensite is more hardenable. But the Jominy test made it easier. So you can see that we have these alloys, and just by looking, you can say that the one that has less drop in the hardness means you get more martensite. You're not going to the martensite, lower bainite, upper bainite, fine pearlite, and coarse pearlite. So it seems it's not been affected. So, or majority of that already is martensite. So this is most hardenable. Even if I cool it very slowly, still I get plenty of martensite. So this is most hardenable. That's one way. So therefore this is most hardenable, less, least. The other way, if you have 10 of them, you want to compare them, relatively you pick a cooling rate, either from here or from here, and then you compare the hardness. Don't pick a very slow cooling rate, because a very slow cooling rate, all of them you may get martensite. You get relatively a little slower cooling rate. That's one way. The second thing is you can see that here now, every cooling rate, which is the Jominy distance, gives you, depends on which alloy you pick, it gives you a hardness. For example, if I cool all these alloys at, let's say, 30 millimeter, each of them gives you a hardness. Obviously, this one does not even meet this. It means that you get the lowest hardness at this point. So that's one thing. Again, I did it schematically. It's not exactly look like the textbook. So each of them gives a hardness. So this is only having three things: the material, the hardness, the cooling rate. But now you might say, okay, well, this material, whatever we talk in this course, the cross section is a bar, a round bar. So you might say, okay, this round bar, but I'm cooling it, obviously, drop this round bar in water. So the surface and the center surface are not cooling the same rate. So there are two different rates. Obviously, the heat dissipated this way. And as a result, the surface has the highest cooling rate and the center has the lowest cooling rate. It is really important to know that what is the regime of phase transformation, because ideally you don't want everything in the surface become martensite, which actually it has volume expansion to get larger, and then the center start to grow, and then there is no room outside, so it's gonna cause cracks. So you would like the center and surface to cool relatively the same rate to get the same structures. So how do I try to embed this concept into the Jominy? Then you have this graph. So this graph in the book, you may get the same kind of scale in exam or anywhere else. You just read it. So 30, I'm just saying that 30, for example, millimeter cooling rate. So you go to, for example, 4340, and this gives you this hardness right here. Okay, let's say, I don't know, maybe about 57. So the same thing here you can do, and you can say that, well, in the 30, so I want to know what would be the proper size for my bar. Obviously, the larger the size is, so the cooling rate is going to be smaller at the surface and at the center. At the surface, you might say, well, it doesn't matter, both of them are in contact with the water, yes, or with the quenching medium. That's correct. But if you have a needle and a 6-inch bar, the thermal capacity of these two are not the same. So definitely it takes longer time for a 6-inch red bar to be cooled down. That's one. And more importantly, the center of the needle is going to be instantaneously quenched, but the center of a 6-inch bar, it takes longer. So now we want to know what would be the proper size. So you want to go and get, based on your design criteria, which in this particular case, there are two things: the material, the second one is the size. You adjust it to get the proper hardness. So in this one, you get, for this, again, purpose of the book, get in the center, so it means right here, half of the radius, which is right here, 3/4 of radius, which is right here, and then you get at the surface. So here is radius, or the center, 0.5, and then here is 0.25 R. So round bar is a solid round bar. For a tube is completely different, but follows the same, different maybe numbers, but follows the same principle. We have to also realize one thing: the larger the bar is, we mentioned that it's going to be slower cooling rate, the smaller is faster cooling rate. If I have to have a minimum hardness at the center, I need to have minimum hardness at the center. It gives me a maximum possible diameter. Because if my diameter becomes larger than my maximum, it means the cooling rate everywhere, including the center, is going to be smaller, and then I won't get the minimum hardness. On the other hand, maximum, and I write here, this gives you the maximum diameter. Okay, so the maximum hardness at the center, it means I want to have not more than this. If it's more than that, it's not going to be good. That gives me the minimum. If I make the diameter smaller than minimum diameter, this will cause that the cooling rate will be faster at the center, which gives me the more hardness than the maximum, which is not. So these two, that gives you maximum and minimum of the diameter. So then you can decide on your alloy. This is number one. Let's do a little bit of just practice here, and then we do something more complex. Imagine I want to get for 4340, and again, very schematic, the maximum hardness at the center of 60, maximum. So look at that here now. 60, I go down here, and it's about 10 millimeter. So let me just erase this. So I want to get for 4340, maximum diameter of, I think my marker is running out of, okay, so maximum hardness of 60 Rockwell C. So that means right away I realize my Jominy distance is 10 millimeter. This is the Jominy distance right here. Okay, so at the center, correct? At the center. Well, then you go in this chart and you say, okay, 10 millimeters like here, right this point, and this gives you roughly around 25. That means, so for getting this 10 millimeter, I need my diameter to be 25 millimeter. This is the bar diameter. So at the here, center, 25 millimeter. If I get, this gives me my minimum diameter. If I do 20 instead of 25, look at that now, like here, then my cooling rate is less than 10, maybe 8, then it's gonna be here, and then it's gonna be more than 60. That's exactly how we use this. So the maximum diameter, in this case, the maximum hardness is 60, the minimum diameter is 25. So I write here the minimum diameter is 25 millimeter. On the other hand, I don't want anywhere in my sample I go below 40 Rockwell C. Okay, for this particular alloy, you never go below 40. But let's say for the sake of argument, I just maybe change a little bit this shape here. And I'm just gonna go, I'm just saying for the again sake of argument, I'll just make it a little bit more drop like this. And let's say 50. I don't want anywhere in my specimen I go below 50. So therefore, the 4340 minimum hardness is 50 Rockwell C. 50 Rockwell C. So when you say anywhere, obviously the anywhere is not in the surface, the anywhere is in the center. Center is where is the weakest link. So center is the lowest cooling rate. So now I don't want to go below 50. And you see now, if I do that here, so I go from 50 here, go like this, meet it here hopefully, and then come back here now down, cooling rate of roughly around 25. So this associated to 25 millimeter Jominy distance cooling rate. And then, so I go to 25 right here, go here, and this gives you something between 50 to 75, halfway through, well, 62 and a half. So this gives you the maximum diameter based on this here. So therefore, 62 and a half millimeter is my maximum diameter. We write here the maximum diameter is 62 and a half millimeter. Now, if this is within range of my design criteria, so I say, well, that's okay. So 4340 is good when using, assuming this is water. Talking about the water and oil, water has a higher H, a faster cooling rate. It's a faster cooling rate environment. If both of them are agitated, still water is good, pound to pound compared with oil. If both of them are stagnant, still is water good. So assuming this is good, I need something between, let's say, I don't know, maybe 30 to 50 millimeter. Then it fits here. There we go. I can use that. It would be good. But what if, and again for waters, but what if this is too large for my criteria? So I need much smaller. So I need, my maximum would be 20 and minimum would be 10. Well, so you need something that it is smaller. Smaller means less hardenable. And that means I use something is not as hardenable as this. I have to make it smaller. Then I use many other alloys, or maybe I change my cooling rate, make it a little bit less heat dissipating from. So I use oil. That gives you a smaller. If this is too small, I need much bigger. My minimum is 50 to 100 or whatever, 50 to 100 millimeter. So in this case, I have a problem because this is not hardenable enough. I have to use a material which is more hardenable than this, which gives me a larger means a slower cooling rate, but I want to get the same regime. So in that case, I have to use either a more hardenable alloy, which I don't have here, or a faster cooling rate, which from here you might go to molten slurry, like a molten salt, which I don't have, by the way, the chart for it in the textbook. These charts are very kind of like academic. So in real life, you work in this industry. They have many. They have center, 90% of radius, 80% go 10 by 10, and you have many different environments and different cross sections. Rectangular, square, tube, hexagon, whatever you can think of. So this part is important for you to understand. Depends on the range. So if the range is too small, So this is too small. In much larger than this range, I have to go to something more hardenable. If the range is too large, I want to go much smaller, I have to use something less hardenable. Just remember these two. So now the next level is to actually use this concept and the diffusion to combine together. So the other concept that we covered in one of those examples was saying that I want, for example, 5 millimeter below the surface, I would like to have this kind of hardness. So when it comes to that question, so you have to realize, okay, 5, for example, 5 millimeter below the surface. So, okay, so what does it mean when it comes to the diameter? So if my radius or my diameter is 60, so 60 millimeter, my radius is 30, and half of the radius is 15, and quarter of radius is 7.5, right? 7.5 millimeter. So therefore, in this respect, 5 millimeter is between the surface and 1/4 of radius if the diameter is 60. If the diameter is 50, obviously things are different. So in this case, it would be 25 millimeter, the radius, and quarter of that would be 6.25, correct? Millimeter. So still, 5 millimeter below the surface is from center to 1/4. But what if F is 50 or 30 millimeter? 30 millimeter. So 30 millimeter, so now the radius is 15, and now what you get is this divided by 4. So it's going to be, I believe, 3.75, right? Yes, millimeter. And this is diameter, radius, 1/4 of radius. So in this case, the 5 millimeter is between half of radius and 1/3 of radius. Then I say 1/4 means 1/4 from the surface or 3/4 from the center. So having said that, for each of these alloys, when it says 5 millimeter below the surface, I want to have this, then you have to go simply, first of all, based on the hardness, you find the cooling rate. Based on the cooling rate, so you want to have this much in the center, this is the criteria. So based on the cooling rate, so you find the diameter, okay? And based on the diameter, you realize that 5 or any number you have, that 5, where is it stands? Okay, it's near 3/4, then you go find the 3/4 here. Then you find for the 3/4, what is the cooling rate? Then you go back to this, based on the alloy, you find the hardness and you check if this is correct. Is it satisfy the design criteria or not? So you have to do it exactly the same order. Repeat one more time. So you want to have at the center, for example, at the center of this alloy, you want to have 50 hardness, okay? And assuming you go check every alloy, but assuming I'm checking 4140. So I want to get 50 here, you go here, there we go. It's roughly around 27 millimeters. So I write here 27 millimeter. This is 4140 for 50 Rockville C. 27. You go 27 here, somewhere like here. And you find here, right, this point, and you see, oh, the diameter is 75. So the bar diameter end up to be 75. So this is right there, 75 millimeter. And then you want to have, let's say, in this case, obviously it's more than 5, but let's say you want to have 10 millimeter below the surface, this hardness. Okay, 10 millimeter below the surface. So you divide it obviously by 8. If it was 80, it would have been 10. So it's, you know, more than below the 1/4. So you go and check what happens in 1/4. 1/4 is this divided by 8. I think it's roughly around 9 something. So you will calculate what is the hardness at 3/4 of the radius. So you have here, you go here 3/4, look at that. This point here, from here you bring it down, and roughly is about 10, for example. Then at 3/4 from the center, or 1/4 from the surface, the Jominy distance is 10. What gives you 10? You go here 10, you go all the way, and you see that 10 is about, I'm saying that, for example, 57. So 57 is the hardness. So if I, for example, want to have the hardness of roughly around 55 at 10 millimeter below the surface, so this one gives you hardness of 57, and this is roughly around 9 something millimeter below the surface. So you want 10 millimeter below the surface, means a slower cooling rate, not by a lot. Then the hardness is going to be smaller than this. If the answer is 55, then you have the correct. If you want to get 60, you will say, wait a minute, I never get 60, because at roughly about 9 something below the surface, again, this is 80. Let's say if it was 80, so then the radius is 40, and 1/4 of radius below the surface is 10. So this is 75. It's about 9 something, like 9 and more. So about 9. So you have the hardness of 75. Definitely at 10, you won't get 60, because the 10 is going to be less than this. Then you can say, well, I can't use this. I have to use a better alloy. I go to maybe 4340, okay? Because then that gives you a better cooling rate. So this is another way. So if we deal about a distance below the surface, and the distance is significantly large, you might say, why I don't use the diffusion? 2 reasons. Number one is 5 millimeter is significant amount of distance, is like 1/2 centimeter for diffusion. It may take months. The second is that maybe even if you do that, the design criteria would not be met. So you have to see, this is one of the criteria, the hardness 5 millimeter below the surface. The next level is now when you have to combine the diffusion with this concept. So now sometimes the question is giving you a set of design criteria, and you realize that, for example, I better use, in this case, 8640. The only problem is that question says 0.5 millimeter below the surface. I want to have the hardness of 65, or very high hardness. So in this case, you will say, Well, I wish it would have not asked about this part because everything was perfect for 8640. Minimum, maximum, hardness everywhere. But this high hardness below the surface makes only one candidate, and that is 8660. So in a sense, I want to have an alloy that this is 8640, but this guy, I exaggerated, which is 0.1 millimeter. This, I wish it was 8660. Well, your wish is granted. There is a way to do it, and that is using diffusion. By the way, you don't go from 8640 to 4360. You cannot change the alloying elements. You only change the carbon content. So these first two digits is the same. I don't have the graph here, but it's similar to 8660, 40, 20, 10, and so on. So this becomes a typical candidate for a diffusion. To get into these two numbers, or these two alloys, you need to go through this process as many times as required. Minimum, maximum distance, chart, everything. But from this point forward, then you have to purely use the second Fick law. So the second Fick law, I write it here. So it's C sub x, remember that? This is the equation. Again, you have to be very, very comfortable to recognize all these values. C sub x is the desirable carbon content at that depth. So what is the desirable? Is 0.6. C sub 0 is the initial carbon content of your alloy. C sub S is the maximum carbon content, which is the carbon content at the surface. Obviously, if this is your alloy and assuming the carbon diffuse in one direction, so from this side, and you put it in a hydrogen-rich gas containing carbon, it's the surface, that very top surface is the carbon content of the atmosphere. So therefore, that is that I have to perhaps calculate or find. This is, it says 0.5 millimeter is 0.5. So this T is the time per second. This D is the diffusion at given temperature. So is D is equal to D sub naught exponential of minus QA RT. Okay. So right now you have temperature, you have time, you have distance, you have initial carbons, and then here we go, maybe another things here. This often in our called carbon is a number, whatever, call it 7.7 minus 3 P another Q RT. Okay, so sometimes for simplicity, we take the T out from there just to make it less, but this is the general equation. Right away, you know what? Right away, I'm just gonna go to a kind of like a back alley to the question in the project is, you said, oh, wait a minute now. It seems I can write in simple but gigantic, not simple, simply can write a gigantic equation which correlates pressure, temperature, distance, and time together. Temperature, distance in this case is constant, but temperature, pressure, and time. These three. And each of them, if associated with the cost, then I have one equation. The cost become a function of this equation, and then I want to minimize that equation, which gives me the money. So that's one way of doing it anyway. But let's get back to this question. So now assuming I have this 0.6, I have 0.4, I have this, everything. So the equation become rather simple. So I'm just going to delete this here and we will continue. So if I write the equation, it's going to be 0.6 minus 0.4 divided by c sub s minus 0.4, 1 minus error function of 0.5, 10 to the minus 3, 2 dt. So hopefully the t is given. I don't want to go more than 3 hours, for example. Then this is going to be 10,800 seconds. The temperature, obviously you have to recognize what is the carbon content here. The initial carbon content is 0.4, for example. You go on the phase diagram, carbon iron phase diagram for 0.4, you find what is the minimum austernizing temperature. And then this has alloying element, therefore it has more carbon than, in a sense, the carbon content is more, and then it's less austernizing temperature you need. But let's stick with the same one, and then you go 30 to 55 degree above that. So you roughly have the temperature. And in this case, obviously, you are talking about the diffusion of carbon in austenite. So D sub naught is given, QA is given, you calculate this D, add the temperature, so you have this. So this is given, everything is given, you calculated this C sub S, which is the carbon content of the gas, and from there you go and calculate simply the required pressure. That's one way. The other way is you go and calculate, you put the 90% or 95% of the pressure at the high temperature, which is the austenizing temperature plus 55, and then you will see what is the surface carbon content. You put the surface here, you have this, you continue and you find the time, and you realize, is the time less than my maximum time? If it is yes, then the problem has a solution. If it's no, then I have to go back and I have to increase the temperature. So temperature has two effects: it increases this and increases this, and then this becomes less. So you're juggling between these. In a real life, you always prefer to minimize time. The only thing is that, first of all, it depends on your facilities. Can you go that high pressure? Can you go to that high temperature? That's number one. And number two is that maybe this geometry is so kind of detailed and it's so intricate that when you go to a high temperature, it changes its shape. And a small spring or something or screw maybe become distorted. That is the design issue. Rather than that, very, very simple. You should have no problem with tackling this question in any way you can do it. So in exam and for the exam purpose, as long as you come up with one answer, that will be sufficient. Maybe not the best answer, maybe the time become maximum, but for that. It would be great if you go a little extra miles if you have time and say, well, you know what, I know there's an answer here, but let me go back here and let me kind of go close to maximize pressure and then redo it, and oh, there we go, instead of 3 hours I'll do it in 30 minutes. That is much more desirable. I certainly hope this covers quite a bit of Jominy and hardenability. I really want you guys understand this completely, clearly, concisely, because this would be definitely related to your more than one question in the final exam. Thank you.